Welcome back, Internet. I'm silly. This is true. I'm very silly in my ability to realize really small mistakes that we all make. It's okay, we all make them. So, today's level is privacy. And privacy is level 12. And in this level, let's check the challenge. So, the creator of this contract was careful enough to protect the sensitive areas of its storage. Unlock this contract to beat the level. Things that might help: understanding how storage works, understanding how parameter parsing works, and understanding how casting works. And a tip is to remember that MetaMask is just a commodity. Use any other tool if it is presenting problems. Advanced gameplay could involve using Remix or your own Web3 provider. Cool. So it looks like our goal here is just to find some sensitive data or sensitive data in storage. Here's the code base here, and there's a really dope cat here. And before we get into the code base, before we touch any of that stuff, we're going to go through the notes per usual to kind of walk you through my thought process, the interesting links I came across, and the things that I've learned, both painfully and definitely meaningful, that I will probably not forget, hopefully. So, first things first is persistence. So this challenge should have taken me probably hour, 2 hours, maybe 3. Took me probably like 8 hours. Reason being is I ran into an issue that I didn't realize was an issue until I figured out the answer. So I felt like this poor man here. I'm not sure if you're much of a philosophy nerd like myself, but this is Sisyphus, and he's pushing the boulder up the hill, and it keeps rolling down, and he keeps pushing it up. And that is the challenge that I've run into, and I'm sure many of you run into when doing anything technical in the sense of programming, auditing, or anything that has to do with building things or breaking things. All right, with that out of the way, I did have to cheat, so we're going to have to give a shout out and thanks to this individual here, who we talked about a lot so far, and that was unnecessary. But yeah, you can see that we have the Web3 blockchain developer guy. He's helped us a lot, and he helped us in this session as well. So thanks to him. Next is we're going to review some of the notes. So the first part of this challenge that you'll realize is that a mistake that some developers have made and continue to make today is assuming that if they've labeled a state variable as private, that means that it's inaccessible and you're unable to see it within quote unquote the blockchain or Ethereum specifically. Now, with that being stated, when this mistake occurs and you've not necessarily encrypted the data prior to putting it on chain or anything like that, the data is accessible to anybody that has access to the blockchain, which is everybody. And with that access means that they can access that private data, even though you think that it's not accessible by others. And to access this and look at it, you have to be able to understand how to look at storage within the blockchain and on certain contracts. And that's where slots come into play. So slots is how data is stored within Ethereum chain. And to actually get access to this, the way that I've utilized, I'm sure there are others, is using the Web3 library, which is something we've used in historical challenges in the same Ethernaut series. And also we've used the get storage app method specifically in previous challenges, and we're going to use it again here to look at that private data. Now, there's a few explanations that I'll send you towards in interesting links. So this one here is not going to play fair, so we're going to have to go into the link here. And it did play fair. Cool. So this is the documentation that talks specifically about get storage app within the Web3 JS library. And this is a specific method that you'll want to use. And you can kind of read through this and understand specifically what parameters are needed, which are optional, and all that stuff. Another useful link that I came across was this explanation here, which I think this individual did a great job. This was written back in 2018, so it's kind of old school, but it's still relevant because this is still how data is stored, specifically in Ethereum. And you can see they basically walk you through in a simplistic manner, talking you through different types of storage and how you can do fixed size values, you can do dynamic values with mappings, you can do more complex values with mappings that have, I think it's, what is it? It's mappings that have struts inside of those, or struts that have mappings inside of those, whichever one. And it kind of walks you through a really good explanation of how to understand that stuff. So I recommend reading this. And there's another video that has this great graphic that I'll walk you through in a second, which comes from another one of our favorite YouTubers. And this one didn't open, so we're going to have to maybe click around some more, maybe it will. Or we'll just do a good old copy and paste. All right, and this video here is a video that we've discussed in a previous challenge, but it's still relevant to this challenge. Smart contract developer, contract person, they do a great job walking you through specifically how to access private data in the blockchain, and they do it in a specific, a different example. So the example that we're walking through is quite simplistic, but this one is a little bit more somewhat realistic, and you have the code base here that they provide. So you can get the code base from their description in their video. So that's another good example to walk through to get a better understanding of how you can access private data within Ethereum. Now, with all it being stated, let's go to this section here. And this is something that's talked about in that video, but I'm going to quickly give you a synopsis here. So here you can see that we're basically going to show you how things are stored within Ethereum. So within Ethereum, there are slots. So each one of these rows is considered a slot for storage. And within storage, there's 256, I think it's bits, that are allowed to be stored within one slot, which I think correlates to 32 bytes. Maybe 64, I'm not sure. Either way, you can see that, yeah, it's 32, I lied. So 32, you can see that we have a bytes, variable that's 32 bytes, and it's called foo, another variable called bar, and both of those are going to be stored in slots 0 and slot 1, because we start from 0 in computer science. So we're going to start from 0, and that 0 is going to be stored here, and that's going to be our foo variable. And then right below that is going to be our bar variable, which is stored in slot 1. And then we have our uint num. So uint is going to default, if you don't put a number here, so you can see there's 32 here. If you don't state that this is uint 8, uint 16, or whatever else, it's going to default to 256. And when it defaults to 256, that means it's going to take up an entire slot by itself. So this uint num here is going to take up the entire thing. And you can see really all that's happened is they put a 7b here for the number that was put in that variable. And then everything else here is padded with zeros. So that's a lot of wasted gas that occurs there. And you'll see with certain smart contract developers, when they're developing things, they'll actually try to order their storage within their Ethereum contract in a way that's more gas efficient. And if they don't, the auditor will hopefully correct them and tell them they should. For instance, if you have a slot 8 and a slot 8 next to each other, those will both go into the same slot. But if you have a slot 8 and then in between these you have a 256 variable, then that's going to take up an entire slot. So and this ends up being 3 slots in total instead of being 2 slots, because if these two 8s were next to each other, they would be able to fit into the same slot. Hope that makes sense, but I will explain more in the actual contract. And then last here we have our address variable, and then we have our Boolean variable. So Boolean only takes up 2 bytes, and then the address takes up, I think this is 16, or no, 32 maybe, I don't know. It takes up half, roughly, the address one. You can definitely do a little Googling and figure out specifically how many bytes that takes up. All right, so that's slots. That is how storage functions within each one of the slots, and that's how you can stack variables together if they're small enough. So the reason that these two are smushed in the same slot is because they're both below 256, meaning they can be smashed into the same slot to save gas. All right, that's good. And then we have some stuff around casting. So this we will talk about. We'll talk about that when we go through the code, because that actually comes into play when we're actually trying to solve the challenge. So here we go. Here is our code. I've added a bunch of comments in here to kind of help me rationalize and logic my way through specifically where things sit. I'll talk you through all those comments. But first off, we got to start with this. I mean, a bunch of super advanced solidity algorithms. This is awesome. When I looked at this, I didn't really understand what it was, but when I put it in VS Code, it made more sense. This is like the cat in space that poops unicorns. Or not unicorns, rainbows. And this is probably the most important part of the video, people. So we're going to look at this. A cat in space, rainbow. So what they showed you there is something like this. I think this is like a famous GIF or meme on the internet webs. But either way, thank goodness that we have the internet. People that are humorous. So this is great, and I'm glad they did that. So kudos to those that made this challenge. All right, next let's look at our code. So in our code, we have our Pragma Solidity version being set up for the compiler version. Remember, this should be 8, not 6. It won't work at 6. And this shouldn't be floating point. It should be static. That's a no-no. Next, we have our contract. So our contract is called privacy. Inside of our contract, we have a series of variables that are being established in the beginning of the contract here. All these comments I've added. So we can see here that the first one is going to be a Boolean variable that's immediately set to true. We have a uint256 variable that's going to be called ID, which is public. So both of these are public, so that means that they're automatically going to have like a freebie complementary getter, so you can actually look at what's in these values because they're public. So this uint256 public ID, and it's going to be in the code. You'll see that this actually says no, this is right. I lied. This is block text timestamp. That's good. Okay, ID is good. Next we have uint8 and uint8. So remember, those are both going to be in the same slot. So these are private. So we can see this is private, and this is private based off of the setup here. And you can see this is a flattening variable. So this is going to be set up to 10, 255, and then this awkward one is going to be uint16, and it's going to be set to now. I made a comment here because when you run this in Remix and you run it with 8 instead of 6, you're going to see that now the I think it's a method or something is deprecated. It's no longer existing. So instead you have to use block.timestamp, and that replaces now due to it being deprecated. So you'll have to put that in there instead of now. And then below that we have another variable being set called data, and it's private, and this is actually an array of 3 items. So that's slightly different than the rest. Now, before I continue here, I want to point out the comments I've added because I wanted to rationalize through what slots are what and what information is stored where based off of the length of the bytes. So you can see that, remember, we're always starting with 0. So this first one here is going to be slot 0, and it's going to be 1 byte. So that's going to be in slot 0. This one here is going to be in slot 1. Reason being is that this is 256, so that means that it's going to take up an entire slot on its own, and that's going to be in slot 1. That's 32 bytes and 256 bits. Below that, we're going to have slot 2 for a few of these. So the reason we're going to have few is because we have 8. This is 8 bits, not bytes. So this is wrong. These are bits, not bytes. All right. And this goes down to the cost, the gas efficiency piece, right? So we have a few uint 8s and a 16. So these 8s are going to be smushed, and the 16 are all going to be smushed together. They're all going to be in the same slot, and that's all going to be in slot 2. So that's going to make this more gas efficient and save the programmer ether when deploying and using this contract. And this last one here is going to be a series of slots. So with arrays specifically, I learned this through the blog that I told you to read, is the first slot, I think should be slot 3, maybe slot 3. If it's not slot 3, it'd be slot 2, where you put in the length of the array. So the first slot's going to be the length. Can't really spell that or look at it, but that first slot's going to be length, and then the remaining 3 slots after that are all going to be what's stored within that array. And this length's going to then point to those arrays when called. So the blog explains it way better than I just did, so check it out. All right, we have our state variables and we have our storage. Next thing is we're going to look at our constructor. So our constructor is going to kick this off and deploy it. It's basically going to take some sort of variable called data. It's going to store it in memory, and then it's going to include it within that 3 bytes array. And it looks like this data that's being put in is probably going to be 3 items that are then going to be stored in this variable called data. Below that we have a function called unlock, and this function takes a key. It takes a key input that's going to be byte 16. It's public, and specifically in here we have a require statement. The requirement statement states that the second slot, or the last slot of the data array, has to be byte 16, and if that matches the key, then you'll change locked to false. Should be set to true. Is it set to true already? Oh, it's set to true already. We want to set it to false so we can unlock it, obviously. Dumb. All right, so it's true currently, and we want to basically pass this require statement. Once we pass this require statement, that means that we can actually unlock the locked currently contract, and then once we've unlocked it, then we win the game and we are celebrating. We're super excited. That is the challenge. That's what we need to do. I will explain this in a second. So we understand the code, we understand the target. This is going to be our attack contract. Very short, very simple. So in this attack contract, we're going to start out with the pragma piece. So we're doing our compiler version, which is 0.8. Shouldn't be floating, should be static. We were going to import the contract here so we can utilize the specific unlock function from there. So we're going to import that here. In addition to that, we're going to have our contract, which is called privacy attack, and we're going to set this, we're going to basically initiate this contract via this target variable. So we're going to call that privacy contract, which is over here. we're going to set it to this variable, and then in our constructor, we're going to add our target address. So this is who we're targeting. And then we're going to take that target address, we're going to initiate that contract, and we're going to add it to this variable here. And once we've done that, in this function, this is where all the action happens. This is where we're actually going to do the unlocking. So when we call this unlock function, we're going to input a slot value. And that slot value is going to have to be the specific array item that needs to be to meet that requirement. And remember down here, the specific item that they're looking for is going to be the last item in this three length array. And the issue that I ran into, and that kept on messing with me, is that I was counting this incorrectly. So this array, when you're looking at it in the state variable section, this is basically stating that there's 3 items inside of that array. It's not stating that there's like 3, it's starting from 0 to 3. It's saying that there are 3 items, 1, 2, 3 in here. But down here, when you're calling it via this data variable and you're putting in the slot location, it's not looking at the quantity of how many are in there, but instead of where it's located. So 0, 0, 1, 2, that is a quantity of 3, which correlates to this 3 here. So what I was doing is I was actually going for the second location instead of the third. So I was basically putting in the wrong slot value, and I kept on putting the wrong slot value, getting a bunch of errors, assuming that it was something else that was the issue, instead of actually me just putting in the wrong value, which is silly and stupid, but that was a hard lesson learned. And that's kind of a thing that you'll need to understand and remember, is that with a computer science, usually within arrays, you start from 0 and you work your way out. I found some interesting notes here that I wanted to share because it was so painful that I wanted to research this even further. So you can basically see this Wikipedia article here. It walks you through specifically what zero-based numbering is and how that works within computer programming. Specifically, they started out within C, and the reason it happened within C, specifically around zero number-based programming, is the fact that pointers and arrays were somewhat similar in nature, and they both had the concept of a zero-based numbering system. So read that if you're interested, but that was a big mistake that I made here that took me many more hours than it should have, but don't make that same mistake. Okie dokie. So we need to put our slot value in here, which is what we'll input, which is going to be that last array variable, but it's going to be it's going to look like the second, but it's actually the last. And then once we put that in there, it's going to put this in the variable key. We're going to then put this inside of unlock, and then we're going to unlock it. One important point to point out here is that you can see that our slot value we're going to input is 32 bytes, but we're going to have to cast that to 16 because within the target address, they're looking for a 16-byte value that's input. And that value that's input, that's at byte 16, we're going to have to cast that. So what we're doing right here is called type conversions or type casting. Now we're going to basically put in our 32. We're then going to cast that 32 into a 16, and then we're going to put that into a key variable that's 16, and that's going to actually suit us and fit what we need to do in that situation to beat that challenge, because we can see here it's looking for 16, not 32. Now there's some links here that help with this and explain kind of what's going on. This video I thought was quite useful. That kind of talks you through type conversions. It specifically talks about it, I think, within C, but it still gets across the point. Oh no, it's Solidity. Solidity, it's good. So it talks about conversions there. And I think there was another link. Yeah, so this link is inside of the docs, and it walks you through implicit and explicit conversions and kind of discusses how you can convert things without intentionally doing so, or you can intentionally do so. And you can sometimes even convert across different types of variables, like, I don't know if it's like integers and variables or something like that, strings. But the thing I wanted to point out here will show you specifically what we're going to do, and it puts it in context. So here we go, that's what I'm looking for. So this specific note here explains to you what casting does to an actual slot value. So here we can see we have uint32 and this is uint16. So we have variable A and B. This is the current slot value that we're looking at, and we're going to cast that 32 down to a 16. So that means we're going to reduce the amount of data inside of that variable, that item that we're sending. And you can see once we kind of look at this comment, once it's casted, that this value is then going to look like this once it's casted down to 16. And what's happening here is when you cast something down from a higher uint to a lower uint, it's going to chop out the first portion of that section. So it's just going to be 0x and then the remaining half of that. Instead of the first half, we're taking the second. And that's kind of the casting downwards, and that's what happens there. And you can see when we cast upwards from a 16 to a 32, instead of taking out stuff, we're going to put in stuff. And you can see they basically injected a series of paddings of 4 zeros to extend that out to a 32 instead of a 16. And that's what we're going to do here is we're going to take that 32, that answer, we're going to chop it in half, put the 0x in the second half portion, and then submit it. And that's how the cookie crumbles. So now that we've talked about all that stuff, I want to make sure I'm not missing anything. All right, that's everything. So we shall solve this challenge. All right, so we can see this here. We've saved it. There's no major errors, so we're good. We're going to apparently save that again because it's not showing up. Make sure that this is inject web 3. What's going on here? There we go, attack. All right, so we need the address here. So if we pull up our panel, remember we're going to do contract.abi just to see specifically what's in here. We can see what's accessible. So the constructor, which we've discussed, the ID, which we've discussed, locked and unlocked, we can see that. So if we run this and we check to see if it's locked, we can see that it's false. It's false because I think I already solved this. So internet, wait a second. I'm gonna get a new instance and we're gonna prove that I can solve this to the world. Okay, so we have our new instance, and if we run this again, we can see that it's true. Okay, this is what it would look like with you once you start. It'll say it's locked and you need to unlock it so you can gain access. So what we first need is the address of our contract. So we can see this is our address. So let's take that from there and put it in here. So when we deploy this, we're going to deploy it specifically to the target that we care about. So that's going to basically put that address in there, and it's going to make sure when you deploy this, that's where you're targeting. That was fast. So it loaded quickly, which is great. So we open this up, and we can see there's one function that we can call, which is unlock, and we're going to put in our slot value. So to get our slot value, if I can remember this, that'd be great. I think it's that. And then I'll explain this in a second once I write it out. Don't worry, I promise. Okay, that worked. Great. All right, so what I've done here is I put in a few things. So we're going to do a wait because that's usually what you do to kind of get rid of the gobbledygook that comes with the pending. We're going to use the Web3.js library. We're going to use the ETH extension, and then we're going to use the get storage method, or the get storage method. And then if you look back at the documentation, you can see there's certain parameters it takes. So one parameter is going to be the address that you're targeting to get the storage from. So that's going to be contract.address. So that's going to be calling this address here. And then we're going to call the fourth slot. I'll walk you through some other slots, but I think it's the fourth or the fifth slot that matters. It might be the fifth actually that we need to win with. And then we're going to do a console.log to pull out that slot so we can see specifically what it is. Now you see, if we kind of go through a few of these, start with the first one. We can see that in this storage, it's set to true, and this is our first variable. So if we go to slot 0, we can see that the boolean of true and false within that hexadecimal array, or that kind of variable, is going to be 1. Now if we do this again, if my computer wants to play nice, maybe we won't. Well, if my computer would let me do what I wanted to do, I would show you, but it's not allowing me. So imagine if you iterated through all of these, you would get to a point where you saw that there was slot 5. And internet, we're going to figure this out, because if it doesn't work, then we can't solve the challenge. All right, so it's working again. Weird. All right, so if I go to the 5th slot and the 6th slot, we can see that the 6th slot is going to be empty. So we know that 5 is the very end. And if it's the very end, that's our answer. Because here we can see they're asking for 2, and that's going to be 0, 1, 2, which is going to be the third item. And that's going to be our answer for the key. So that being stated, we just need to copy this and put it into our attack. That's specifically the location that we're going to attack. So once we've put in that specific slot, what it's going to do is it's going to cut it in half with a byte 16, so from 32 to 16. It's then going to inject that into our key, and it should give us the right answer. So if we come back here and our computer breaks again, we'll try to get this to work. Cool. So now we want to check if it's locked again, and we can see that it's false. So if we submit our instance, we should, in theory, have beat the challenge. And we beat it. Congratulations, Internet. This is the privacy challenge. So I'll see you on the next level, which is Gatekeeper 1.